Hi, my name is Ragnhild Aurlien, and I'm doing my PhD at the University of Oslo, where my main focus is on future CMB satellites. So today I'm going to talk about LiteBIRD, and first a bit about the experiment in itself before I explain how we use Commander for future experiments. So this is the last picture taken in the last physical meeting in 2019. The collaboration consists of more than 300 researchers from both Japan, North America, and Europe. You can see the flags from the different countries contributing here. And it stands for Light Satellite for the Study of B-Mode Polarization and Inflation from Cosmic Background Radiation Detection. So it basically says what it's meant to do. And it's led by JAXA. So JAXA is a Japanese space agency. And they selected LiteBIRD as their L-class mission in May 2019. And the plan is to launch it in the late 2020s with the rocket that you can see pictured here. And it will be launched to the Lagrangian point L2, where it will observe the microwave sky for 3 years. And it will do so with 15 frequency bands between 40 and 402 gigahertz, with an angular resolution between 70 and 18 arc minutes. So it's not super high resolution, but it's designed to measure the B modes, which are on big scales. So that's not a problem. Yes. And just to make sure that you know what I will talk about when I talk about the B modes and cosmic inflation and gravitational wave from Big Bang, I'll just give you a repetition. So here you see the classic picture of the Big Bang expansion. So you started with quantum fluctuations, and then you had a very short period of exponential expansion. And it's expanded by a factor of 10 to the 26, which is like you take a needle, like the top of a needle, and you expand it to way larger than out to the Andromeda galaxy in such a short time frame, like 10 to the minus 36 to 10 to the minus 32 seconds. So it's incredibly fast. And this is then causing gravitational waves. And then blah, 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 a lot of things happened. And then 370,000 years, we have recombination where the cosmic microwave background radiation was released. So as I said, inflation created gravitational waves. And these are the gravitational waves we want to detect. And they can be observed with a pattern called B mode. So if you see the like you have blue spots and red spots in the CMB, and you see around them, you see the direction of the polarization. Then you have, like, if you have circles or straight out, that's E modes, it's curl-free pattern. And B modes, they have like this curly pattern. And this is the signal that we're looking for. And it's measured by R, which is the tensor to scalar ratio. So how much B modes we want, like we detect, that's kind of how large is the difference between these two. So here you have a power spectrum where you have the variance in the CMB maps and the y-axis, and at the x-axis you have the multipole or the angular scale. So here you have simulated level of inflationary B modes where r equals 10 to the minus 2. Actually, it is like some of the leading inflationary theories say that it's more like 3 times 10 to the minus 3. so even lower than this. So this is how much of this signal we expect to find. And then you have the E modes up here. And you kind of have the how much do you have of one of them compared to the other. That's basically what R is. And the current best constraint, so we haven't done any detection, but BICEP and the Keck collaboration, they recently, just a couple of weeks ago, released that they have an new upper constraint on 0.036. So we're quite far off from that to 3 times 10 to the minus 3. So detecting this B mode signal, that's the main goal for LiteBIRD. Or if we can't detect it, then at least we can rule out a lot of well-known and well-motivated inflationary models. And you can see here that you have like data from Planck. Planck did very well in temperature and quite well in the E modes, and then, but not at all in the B modes. And then you have all these other experiments, for instance, BICEP and Keck, but they are only measuring on higher L's. And the black dots here is LiteBIRD, how well we will be able to measure this. And we will be able to detect both the reionization bump, which is this bump, and the recombination bump, which is this bump here. And that is without any external data. And LiteBIRD is also able to do a lot of other things, like other discoveries. I won't go into detail, but we'll get a huge data set, which hopefully will give us a lot of new physics. Like, of course, you will get better measure of the E modes as well. You can get better estimates of the neutrino mass. You can study cosmic fire fingerings and Z effect, etc., etc. I won't go into much details, but if you're interested, then pause and have a look at this slide. So here you have the LiteBIRD scanning strategy. So it'll rotate both in that, like 2 different ways simultaneously. You have the sun and the Earth, and here is the L2, and you will measure the CMB. And this is estimated heat map for the 3 years. So you see, like, you'll have some parts where you hit the sky more often than others, of course. And LiteBIRD consists, like, this is the newest design for LiteBIRD. It consists of 3 telescopes, the low, medium, and high frequency telescope. And that's 3 halfway plates, so they're rotating halfway plates. And they, by having rotating halfway plates, you can get rid of a lot of correlated noise and systematic effects, which is great, because we really need, because these B modes are really, really weak. It's a ridiculously weak signal. So we need an extremely well good control of both the systematic effects and the noise and the sky and everything. So for LiteBIRD, we use both Commander 1, Commander 2, and Commander 3, and we do something called forecasting, which is given how much noise we will have per frequency band and the other specifications from the instrument design, we simulate the sky. How this will, like, how we will then be able to observe the sky. And then we try to go backwards and get back the signal that we put into the simulations. And if we're not, then we have to change the telescope. So that's LiteBIRD is a bit further than that, but that's kind of basically the idea. We have to make sure that with the instrumental specifics that we have, we're able to actually do the detection that we're aiming for. So map-based simulations and time-ordered simulations, that we're doing both. So I'm going to focus on the time-ordered simulations. So you can see here just a simulation of 1 hour of data. And we then base this on the noise levels, and you have already foreground maps like that we have from previous experiments. Simulate CMB, and then based on the scanning strategy, etc., then we generate these simulations. And then Planck, like as you probably heard already, analyzing the LFI data. So for Planck, then we're basically at the limits of our computational resources today. And LiteBIRD will have more like 10 terabytes of memory required. So to be able to run time-ordered data through Commander 3, we scale down the number of detectors and the noise level accordingly, so that the total sensitivity will be still full mission, as the design says. And then I simulated TOD based on simulated sky. So you can first make map-based simulations and then kind of scan those maps as it were the real sky. And I use a code called Genesis. And I then run this time-ordered data through Commander. So you have a pipeline kind of here. So after making the simulations, I do a Huffman compression, and then of course simulate RMS maps, beam files, instrument files, etc., and put it all into Commander, and get output as you normally do with Commander. So here's some of the results. Here's 1 hour of data for one frequency. So you can kind of see how the scanning pattern goes. And this is with 24 hours of data. Still with just one frequency, so you can see that already there's pretty good sky coverage with just like 1 day. And LiteBIRD is going to observe for 3 years. So here's an RMS map for after 1 year of scanning. So you can clearly see the scanning strategy. So the lower value means that you've hit that pixel the more times. So you can get all these things from simulated data. And here are just 4 frequency maps. So you have 40 gigahertz, 68 gigahertz, 100 gigahertz, and 402 gigahertz, where the simulations consist of CMB, thermal dust, and synchrotron, and noise. And this is just a frequency match. I've not done any component separation, just removal of 1 or F noise. And you can see especially clear here on the 68 gigahertz, the flickering that's moving between different samples. So you can see that you can here already see how different removal of the 1 over F noise, how that will propagate through our whole pipeline, also with simulated data. So with real LiteBIRD data, Commander can be used to do iterative analysis of the data, all the way from the TOD to the cosmological parameters, because we assume that we have a functioning command tree where you also estimate the cosmological parameters within 10 years. You can also add other data sets, and that you can do either in map space or in time domain. And by doing so, you can improve the component separation. During the forecasting process, which is now before launch, you can add, so the time or the day that you saw, that was just like very simple model, but you can also add systematic effects, like how will this do, like how will this systematic effect or this systematic effect propagate and affect our measure of R. That and of course, Commander can also be used to generate the time or the data itself, like the simulations. Okay, that's what I was planning to say. So thank you and good luck with your course.